2.5 million years ago, there were no humans on this planet. There were no cities, no language, no fire. Our ancestors were small, frightened creatures walking upright for the first time on the plains of Africa. Looking up at the sky they had no words for. And somewhere, impossibly far away, a star died. In its final moments, it relays something, a particle of light, a photon, moving at 300,000 kilometers per second through absolute darkness, through the void between galaxies, through 2.5 million years of empty space, completely alone. No destination, just light, traveling. Last Tuesday, that photon landed on my laptop screen. I want to start with a question, not a technical question, not a coding question, a human question. Have you ever looked up at the night sky, really looked, and felt something you couldn't name? Not fear exactly, not loneliness, something closer to a vertigo. The sudden sense that you are very small, and the darkness above you goes on forever. And somewhere out there, something extraordinary is happening right now, and you have absolutely no idea what it is. I felt that my whole life. I felt it as a kid, lying on my back in the garden, staring up, wondering. I wanted a telescope more than almost anything. I never got one. Not because my parents didn't care, they did. But telescopes were expensive, and even if I had one, what would I have actually done with it? Looked at a blurry moon? Tried to find Saturn's ring on a cloudy night in a light polluted city? So I grew up. I studied, I built a career, I had children of my own, and somewhere along the way it happens to most of us, the sky got smaller. Not literally, but in my daily life. The inbox got bigger. The meetings got longer. The night sky became something I drove under without looking up. Until about 3 months ago. I was reading about the James Webb Space Telescopes, the new images it had been producing. Galaxy from the early universe, when the cosmos was only a few hundred million years old. Stellar nurseries, nebula no human eye had ever seen before. And I felt something I hadn't felt in years. That kid, still there, still wondering. But this time, something was different. Because I am an engineer, I know a little bit of Python, and I started asking a question I had never thought to ask before. Where does that data go? When Hubble takes an image, when JWST captures a galaxy, when a telescope detects a faint dip in a star's brightness that might be a planet passing in front of it, where does that data actually go? I assumed it went to scientists, to universities, to government computers somewhere behind locked doors, accessible only to people with PhD and clearance badges. I was wrong. Here is the thing that stopped me completely. NASA publishes the raw data from almost every measured telescope. Free. Available to anyone. With a browser and a basic knowledge of Python. The telescope I never had as a kid? I have had access to hundreds of them for years. I just didn't know how to read what they were saying. That changes tonight. I want to give you the epiphany before we write a single line of code, because the code is just a tool. What matters is what the tool reveals. We are living right now in the most extraordinary moment in the history of human observation. Let me show you what I mean. For most of human history, if you wanted to study the universe, you needed a mountain. You needed a dome. You needed a mirror the size of a living room. You needed a team of engineers, decades of founding, and a career devoted to nothing else. The knowledge of the cosmos was locked behind institutional walls. Galileo had to build his own telescopes to see Jupiter's moons. Hubble had to fight for access to the largest instrument on Earth just to prove that other galaxies existed. Even 20 years ago, if you wanted to study a galaxy, you applied for telescope time, you waited months, you got maybe one night of data if you were lucky. And now? Right now, in 2026, you can open a browser, type 4 lines of Python, and download a scientific observation of the Andromeda Galaxy that took a real telescope, a real exposure time to produce, in about 30 seconds, for free. The data that professional astronomers use it to fight over is sitting in public databases, waiting for someone curious enough to ask for it. That is not a small thing. That is one of the most remarkable shifts in the history of science. The democratization of the cosmos. And almost nobody knows it's happened. You do now. Before we touch the code, I want to tell you about what we are actually looking at tonight, because the numbers are almost impossible to hold in your mind, and that's exactly why you should try. The Andromeda Galaxy, M31. Our nearest large neighbor in the universe. It is 2.5 million light years away. One light year is the distance light travels in an entire year, at 300,000 kilometers per second for 365 days, without stopping. That is one light year. Andromeda is 2.5 million of those. The photons we are going to process tonight left Andromeda before our species existed, before the first human made fire, before the first word was spoken, before any of recorded history, any civilization, any monument, any written language, those photons were already halfway here. They crossed the void between our galaxies, which is not empty. There are few stray atoms per cubic meter, but essentially nothing. For 2.5 million years. Entered the Earth's atmosphere, hit a telescope, became electrons, became numbers, were uploaded to a public database run by NASA, and tonight we are going to turn them back into light. One more number, because it matters. Andromeda contains approximately 1 trillion stars. Our own Milky Way has roughly 300 billion. Andromeda is bigger than us, and it is heading toward us right now at 110 kilometers per second. In approximately 4.5 billion years, Andromeda and the Milky Way will collide and merge into something new, a galaxy with no name yet. The photons from that collision haven't left yet. We'll be ready. I have 10 steps to show you tonight, and I want to make you a promise before we even start. You do not need to understand the code. I mean that. A cardiologist doesn't explain the circuitry of an ECG machine before reading your heart. The machine is just how we listen. Tonight, Python is how we listen. What matters is what we hear. Step 1. We install our instrument. 3 libraries, each one a different kind of ear. AstroPy reads the language of telescopes. AstroQuery connects us directly to NASA archives. PhotoUtils measure the brightness of what we find. While that runs, I want you to think about what is about to happen. We are going to reach across the internet into a database maintained by NASA and pull a real scientific observation of a galaxy 2.5 million light years away. Not a photograph someone took, a measurement, a record of exactly how many photons arrive at a detector from that direction in the sky on a specific night through a specific instrument. We are in step 2. We load the tools into memory. One of these, SkyCoord is how Python understands a position in the universe. Not a street address, a direction in space, expressed as two angles. That has been the same since before any human was alive to write it down. Every object in the sky has one. Andromeda's address hasn't changed in 2.5 million years. We are about to use it. Step 3. Write ascension 10.68 degrees, declination 41.27 degrees. Python just queried the catalog maintained by astronomers in Strasbourg and returned the precise address of the Andromeda Galaxy. The same coordinates every professional astronomer uses when they point a real telescope at M31. We are pointing ours now. Step 4. This is the moment. We are reaching into NASA SkyView service, a virtual telescope, and asking it to send us a real observation of Andromeda from the digitized sky survey. Real photographic plates, real telescopes, real exposure. Decades of real observation, digitized and now available to anyone with a Wi-Fi connection and 4 lines of Python. It's here. Step 5. We open the container. The data is stored in a format called FITS, the Universal File Format for Astronomical Data since 1981. Think of it as a scientific box. Inside, 2 things. A header, every detail of the observation. Telescope, date, coordinates, exposure time, everything needed to reproduce exactly what was seen. And data, a matrix of numbers. Each one a photon count. Each one the end of a 2.5 million year journey. Step 6. We meet the data, 1,000 by 1,000. 1 million individual measurements. Look at the minimum and maximum values. See the gap? That is the dynamic range of the universe. The bright core of the galaxy is orders of magnitude brighter than the fade-out regions. If we display this data as it arrives, the bright parts dominate, and the faint structures, the ones that tell the real story, vanish, which is exactly what we are about to see. Step 7. The raw data. Dark. Almost nothing visible. And I want you to resist the instinct to be disappointed, because this is honest. This is what the universe looks like before you know how to listen. The signal is there. The photons are there. 2.5 million years of travel stored in those numbers, waiting. We just need to amplify it. There she is. Same data, same numbers, same photons. We apply the square root transformation, which compresses the bright regions and amplifies the faint ones. And a galaxy was invisible a moment ago is now unmistakable. This is not manipulation. This is not making something look better than it is. This is the same things your eye does when you walk from bright sunlight into a dark room, adjusting how you sample the light. We didn't add anything to the data. We learned to see what was already there. And what was already there is a galaxy of 1 trillion stars. Those faint extensions you can see reaching outward from the bright center. Those are stars in the outer halo of Andromeda, individual stars in another galaxy, 2.5 million light years away, visible now because we changed how we listened. Step 9, we go deeper. We are looking at the galactic core now, the oldest, densest, most ancient region of Andromeda. In here, the stars are packed so tightly that if you lived on a planet orbiting one of them, your night sky will blaze with 1,000 suns. Every bright point you see in that image, every single one, is a star or a cluster of thousands of stars gravitationally bound together, orbiting the galactic center as a single object. Andromeda has approximately 460 known globular clusters. Some of them are in this image. Right now. Step 10. Look at it. This image is yours. Not downloaded, not screenshotted, not found anywhere online. Derived from raw photon measurement by you tonight. Let me tell you what actually happened tonight. A photon left a dying star in the Andromeda Galaxy 2.5 million years ago, before our species existed. It crossed intergalactic space alone for longer than our entire evolutionary history. It entered the Earth's atmosphere, hit the mirror of a telescope, became an electron, became a number, was uploaded to a public database run by NASA. And tonight, in a home office, after the kids were in bed, with one free browser tab and 10 lines of Python, we turn it back into light. We completed its journey. I keep coming back to something. We talk about the democratization of technology as if it is a future promise, as if it is something that is still coming. It is already here. The telescopes that used to require a career and a mountain and decades of funding are sitting in public archives right now. Hubble, Kepler, TESS, the digitized Sky Survey, Gaia, a catalog of 1.8 billion stars with precise position for every single one of them. Free, open, waiting. The question is not whether the data exists. The question is whether you are curious enough to ask for it. I have been thinking about that kid, the one who wanted the telescope. He thought the barrier was equipment, money, access, a clear sky. He was wrong. The barrier was knowing what to ask for. You know now. Next episode, we are going to make an image that looks like the ones that stopped the internet. 3 Hubble filters, combined using the exact technique NASA uses to produce those iconic color images, the pillars of creation, the deep fields, the images that make people stop scrolling and just look. We are going to build that from scratch in a free browser tab. If you felt something tonight, subscribe, because the universe has a lot left to say, and we are just learning to hear it.